cosmos, space, and time travel, science and technology. Brought to you by theoretical physicist, futurist, popularizer of science, and world-renowned author, Professor Michio Kaku.
And GCNlive.com.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile some of the most amazing developments in science and technology. And with us once again, we have a special guest, astronomer Ken Croswell, who will talk to us about some of the latest things in the heavens. Did you know that the Arecibo radio telescope, that giant radio telescope used as a prop in James Bond movies and also the movie Contact, it's been the workhorse for people interested in what's out there in outer space. It's going to be junked. That's right. 2 cables snapped recently, and the National Science Foundation has said that it's simply too dangerous to fix it. So one of the most iconic instruments of science will be mothballed. And then let's talk about meteor showers. Did you know that there's a meteor shower coming your way? Maybe you've never seen one. They're quite spectacular. And we'll talk to astronomer Ken Croswell about that. And speaking about astronomy, some astronomers are not too happy with SpaceX. SpaceX has been making headlines, pioneering cheap, disposable rockets that can be reused over and over again. And SpaceX wants to put maybe 1,000 mini satellites into orbit. And some astronomers are saying, what does that mean for the night sky if every time you photograph the night sky, you bump into one of these mini satellites? Well, once again, with us today is astronomer Ken Croswell of Berkeley, author of Alchemy of the Heavens and a number of great books. And if you want to know more about Science Fantastic, go to my website, mkaku.org, mkaku.org. I've written 4 New York Times bestsellers, and I have about 4 million fans on Facebook. So let's just jump right into it. Once again, our special guest today is astronomer Ken Croswell of Berkeley. Well, leading off, the Arecibo radio telescope, one of the workhorses of radio astronomy, is being junked. Not one, but 2 cables snapped, collapsing the radio telescope. It's an iconic telescope seen in movies. Maybe you've seen the movie with James Bond and also with Jodie Foster, Contact. I visited the Arecibo radio telescope when I was in Puerto Rico once, and it is incredible. You go up an elevator shaft all the way to the top, and there you see this gigantic radio telescope, bigger than a football field, and you almost feel like you're communing with the stars, because this radio telescope can receive signals from distant star systems. So, Ken, first question is, what was your reaction when you first heard that the radio telescope in Arecibo, Puerto Rico, is going to be mothballed? What was your first impression?
Well, I was sad to hear it was going to go away. As you know, it has just recently collapsed, so there's just no way that instrument is going to be able to do what it had been doing. As you may know, the very first planets discovered around other stars were discovered by the Arecibo telescope back in 1991. Alex Boshin used that telescope to discern variations in radio waves coming from a pulsar in the constellation Virgo. And he discovered 2 and then later a 3rd planet going around that pulsar. Those were the very first planets discovered outside of our solar system. And it was the Arecibo the Arecibo telescope that did it. So, yes, it's definitely disappointing. Of course, there are many other radio telescopes here on Earth. Radio astronomy is very important to astronomers because it probes a whole different wavelength range from visible light. So we learn things in radio that we don't learn from visible light, just as we learn things from visible light observations that we don't learn from radio observations. So, yes, it's sad, but, science moves on, I guess you could say.
And speaking about radio telescopes, recently radio telescopes were latched together to give us the first photograph of a black hole in the galaxy M87. So how was that done? How do you latch together several radio telescopes to get the effective radio telescope of one gigantic radio telescope the size of the planet Earth, capable of photographing the event horizon of a black hole way out there in outer space? How does that work?
Well, this is something that's really nice and is much easier to do with radio waves than with light waves. It's called interferometry. You're able to link together separate telescopes, and you get a higher resolution, a higher sharpness of the resulting images. And the reason that's so much easier to do with radio waves than with light waves is because the radio waves are big. Sometimes they can be inches or feet or even yards in size. And so the precision with which you have to line up your telescopes only needs to be about as precise as that wavelength. In contrast with optical light, with visible light, the wavelength is so tiny and it's microscopic. You have to line up your telescopes as precisely as those tiny, tiny wavelengths. And that's why optical interferometry is much harder than radio interferometry. But radio astronomers have been doing interferometry for decades. There's an array in New Mexico, a very large array, the VLA, and that has been doing interferometry for a very long time. And in fact, that array helped to confirm the planets around that pulsar I mentioned a few minutes ago, because it measured a more precise position for the pulsar in Virgo in order to pin down whether the variations in its radio waves were indeed coming from orbiting planets. And indeed they were. That pulsar has 3 planets we now know of, and it was the Arecibo radio telescope that discovered it.
Now, let me ask you about the advantages of radio telescope over optical telescopes. The galactic center, the center of our galaxy, should be a fireball illuminating the night sky, because it's at the center of the galaxy. But when you look in the direction of the galactic center, we see nothing. It's all covered up with dust clouds. So how do we know so much about the galactic center? Is it because radio telescopes can pierce through all the dust and debris that separate us from the galactic center?
Yes, that, and also infrared observations. Both infrared and radio waves have longer wavelengths than visible light, and it turns out that those longer wavelengths are able to penetrate the dust that blocks the visible light from the galactic center. If you look at the galactic center, you can tell that there's something going on there. You know, even at optical wavelengths, you see that there's more starlight in general coming from that part of our galaxy. But in terms of actually looking at these stars that are going around the black hole at the center of our galaxy, you need infrared observations, which track those stars. Also, the radio observations tell you about the gas, because gas, interstellar gas, emits radio waves. That's one of the biggest advantages to using radio telescopes, is it maps the gas. And in fact, you've, I'm sure, heard of the 21-centimeter line, which atomic hydrogen gas emits. We can track that throughout the Milky Way galaxy. We even see it in other galaxies. That's because it emits radio waves from all over the galaxy, and we can detect them.
So isn't it true that when we made the transition to radio telescopes, that really opened up a whole new realm of the universe that we could not see with optical telescopes, which are largely obscured by dust clouds and debris and stuff like that? So didn't that create a whole new renaissance, especially after World War II, when this technology was perfected?
Yes, every time we look at a different wavelength of the...
Okay, we have to take a short commercial break, but after the break, we're going to continue a discussion of radio telescopes and meteor showers. Have you ever seen a gigantic meteor shower lighting up the night sky? Here's your chance. And once again, you are listening to Science Fantastic with Professor Michio Kaku. Give us a call, 612-564-8135 is the number to call if you want to ask a question on National Radio. give us a call. Welcome back to Science Fantastic with Professor Michio Kaku. With us today is, once again, astronomer Ken Croswell, author of a number of great books, including Alchemy of the Heavens, Magnificent Mars, The Universe at Midnight, a number of great books. And once again, we're talking about the universe, what we know about everything that's out there in outer space. Now, before World War II, of course, we had optical telescopes, but unfortunately, a lot of the universe is obscured by dust clouds. At the very center of our galaxy, there's a raging black hole with in the galactic nuclei, which should be a fireball that lights up the night sky, comparable to the moon in terms of intensity. And yet, when you look in the direction of the Milky Way galaxy, what do you see? Almost nothing. Dust clouds obscure the way, but radio telescopes allow you to pierce right through, to track stars, to track the center of the galaxy, and it's opened up a whole new realm of information about the universe. But unfortunately, one of the workhorses for that revolution, the Arecibo radio telescope, well, unfortunately, it's going to be mothballed. Not one, but two cables snapped recently, and it's simply too dangerous to allow workers to repair that radio telescope. And some people think that's a tremendous loss. Now, isn't it also true that the Arecibo radio telescope has opened up the world, as you mentioned, to exoplanets, not just black holes, not just supernovae, but also exoplanets that are orbiting other star systems?
Yes, indeed. As I tell the story in my book, Planet Quest, it was the Arecibo radio telescope that discovered the very first planets going around another star. Alex Volshin was using that telescope. Ironically enough, he discovered the pulsar because the radio telescope was broken at the time that he was conducting his observations. He wanted to look for a particular type of pulsar far away from the galactic plane, which is not a place where these particular pulsars tended to be found. And it was only because the radio telescope at Arecibo was broken, it could only look at whatever part of the sky happened to drift overhead. And in doing this, he actually discovered two pulsars. One of them turned out to be quite interesting because it helped test Einstein's general theory of relativity, because another neutron star was going around that pulsar. But the greater harvest was his discovery of this pulsar in the constellation Virgo that turned out to have three planets, and those were the very first planets ever found. Two of them were found in 1991, and the third one was found in 1993. So Alex Volshin and Dale Frail made that discovery back in the early 90s. That was before we had actually detected any planets around ordinary stars. The very first planet detected around stars like the Sun, that came in 1995, around the star 51 Pegasus.
So not only did the radio telescope at Arecibo give us an inkling about what lies behind the dust clouds, black holes, exploding stars, not only has it given us information about planets orbiting other star systems, but it's also given us some indication that maybe, just maybe, one day we'll find indications of extraterrestrial communications. This is the SETI project, the Search for Extraterrestrial Intelligence. We've had a number of those people on the radio waves, but Ken, let's be honest. The radio telescope at Arecibo and around the world, have they ever picked up just one reputable, verifiable communication with an alien civilization in outer space? Yes or no?
No, not at all. And in fact, that actually convinces some people that maybe these aliens don't exist, or if they do exist, they're pretty rare, or if they're not rare, maybe they're sufficiently smart to keep their mouths shut and not let the rest of the universe know about their existence. So, no, there has been no detection of any aliens via radio waves or any other form of radiation.
And as a side note, there's something called the METI project, which actually wants to use radio telescopes like the one at Arecibo to shoot messages saying, here we are alive, we're Earthlings, third planet from the sun, and advertise our existence to aliens by shooting shooting a radio signal that says, here we are. Now, do you think that's a good idea? The late Stephen Hawking thought it was not a good idea, pointing to what happened to the Aztecs when they met Cortez and his men. What are your thoughts?
I think advertising our presence to the rest of the universe is a really dumb thing to do, because other civilizations could be much more advanced than ours and could snuff us out if they wanted to. We have no indication whatsoever, of course, that there are any civilizations out there, but if there are, we have no idea if they're friendly or hostile. So it would be prudent for us to keep our mouths shut. That's my opinion.
Okay, well, let's also talk about meteor showers. One is coming our way. Maybe you've never seen a meteor shower before. They're quite spectacular. So tell us a little bit about the Geminid meteor shower that our viewers may be able to detect.
Yes, I have the cover story in the December 5th issue of Science News. It's all about the Geminid meteor shower. And this is something that you can see without a telescope. You don't need to know where the constellation Gemini is. All you need is a dark sky. Avoid light. If you need light, try to use a red flashlight. Red light is not as bad for your eyes as white light is. And these meteors will peak on the night of December 13th. That's a Sunday night going into Monday morning, the pre-dawn hour. We can expect at their strongest, the Geminids will give us over 100 meteors an hour. That's if you're away from city lights, got dark sky. The reason this year is so fantastic is because the moon is new on the night of December 13th. So the moon will not interfere. The moon will not wash out the meteors. So conditions this year are really good. The interesting thing about the Geminids, aside from their strength, is that they come not from a comet, but instead from an asteroid. Most meteor showers, such as the Perseus in August, they come from debris shed by a comet. The Geminids were the very first meteor shower linked to an asteroid. In 1983, the infrared astronomical satellite detected a small asteroid, now named Phaethon, that is the source of the Geminid meteor shower. It sheds particles into space somehow and produces the meteoroid stream. When those particles burn up in our atmosphere, we see the streak of light, which is what's called the meteor. If any of those particles actually make it to Earth's surface, the resulting object is called a meteorite. So when they're drifting in space, these particles are called meteoroids. The flash of light you see when they burn up in the atmosphere is called the meteor. And if any of it makes it to the Earth's surface, that's called a meteorite.
And roughly speaking, how big are these chunks of rock and debris that are hitting the Earth? Roughly how big are they when they hit the atmosphere? Most of them, of course, burn up and never reach the Earth. But how big are we talking about? A basketball, a pebble? How big, roughly speaking, would some of these meteors be?
Most of them are smaller than a dust grain. So these meteoroids are very tiny. The typical meteor that you see is coming from a very small particle. However, the very brightest ones, for example, what we call fireballs, these are meteors that are brighter than the planet Venus, those are coming from larger objects that probably can make it through the Earth's atmosphere. But the vast majority of these meteors are coming from very small particles, smaller than a dust grain, smaller than a sand grain.
And isn't it true that we don't really track these things unless they're, let's say, much bigger than a football field? And most of those asteroids are pretty safe. They're not going to hit us anytime soon. But the smaller ones smaller than a football field, one just bypassed the Earth just a few weeks ago, and we were blissfully unaware of the fact that an object about the size of an apartment building was slowly drifting in our vicinity, closer than the radius from the Earth to the Moon, but totally unobserved, totally unnoticed by our sensors. So doesn't that make you worried that one day we may get caught off guard by a piece of debris floating in outer space with our name on it?
Well, the small ones are hard to find because they're so unprominent. But Phaethon is actually considerably larger. It's about 4 miles in diameter, as was revealed by the Arecibo telescope that we have been talking, because the asteroid came close to Earth.
Okay, Ken, let's take another short commercial break. Once again, you are listening to Science Fantastic. Give us a call, 612-564-8135 is the number to call if you want your thoughts to be heard on almost 100 radio stations that carry Science Fantastic. So, give us a call. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is astronomer Ken Croswell of Berkeley, author of a number of great books, including Alchemy of the Heavens. And when we last left off, we were talking about meteor showers, especially when the Earth goes through the debris trail of a comet or a passing asteroid, and you can catch it in the next few days. And once again, it's a Geminid meteor shower. Now, by the way, I was looking up the history of meteor showers the other day, and back in the 1800s, there was a fantastic meteor shower that freaked people out in colonial and frontier America back then. And it was so great that it spawned religious groups who thought that it was a prediction of doomsday and the second coming of Jesus Christ. And many of these sects, religious sects that developed, splintered. Some of them became precursors of things like Jehovah's Witnesses and Seventh-day Adventists. So it turns out that the religious history in America was in part fertilized by sightings of gigantic meteor showers in outer space. So Ken, once again, for those people who tuned in late, tell us about how the average listener out there can see a meteor shower.
Okay, well, what you need to know is that the peak of the meteor shower is after 10 p.m. on Sunday night, December 13th, on the night of December 13th. Go out, away from city lights after 10 p.m., after midnight's even better, and just look up and avoid any lights, especially avoid any white lights. If you need lights, try to use a red flashlight, and give your eyes plenty of time to adjust to the dark. 20 minutes is ideal, so don't just go out for a few minutes and think you'll see something. You need to give your eyes at least 20 minutes to adjust to the dark. So again, Sunday night, December 13th, after 10 p.m. Excellent reason to violate curfew in the event you live in a state where there is curfew imposed. So look up, get away from city lights, and just look wherever the sky is darkest. You don't need to know where the constellation Gemini is, because meteors will appear all over the sky. At the peak, you should be able to see about 100 meteors an hour. If you're lucky, you might see even more than that. But the most important thing is the sky must be dark and your eyes must be dark adapted, and avoid light.
And the meteor shower, as you mentioned, is because we're going through the debris trail of an asteroid. So does this happen every year? Every year does the Earth go through the debris trail of a comet or asteroid?
Every year at that time, yes. The Earth does go through that asteroid's debris trail. However, this year is especially good because the moon will not interfere. The biggest enemy of meteor observing is moonlight, because moonlight washes out the meteors. Of course, clouds also block your view of the meteors. So those are the two enemies of meteor observing, the moon and clouds. But, I can't predict what the weather is going to be like on the night of December 13th, but I can tell you that the moon will not be interfering whatsoever. So conditions in the sky are going to be absolutely perfect on the night of December 13th. Again, after 10 p.m., just go out where it's dark and look up.
Now, there's no danger from these things because the United States tracks, astronomers around the world track the objects, near-Earth objects, that are perhaps larger than a large football field. However, things smaller than a football field can also create tremendous amount of chaos on the planet Earth, and we don't track them. So isn't it possible, well, let's take a short commercial break, but isn't it possible that we can be caught off guard by one of these smaller asteroids and create all sorts of havoc? Once again, you're listening to Science Fantastic with Professor Michio Kaku. After the break, we're going to continue a discussion of meteor showers and a new planet in the solar system. Stay tuned for Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. Once again, if you want to know more about Science Fantastic, go to my website, mkaku.org, mkaku.org. And with us today, once again, is astronomer Ken Croswell of Berkeley, author of Alchemy of the Heavens and a number of other great books. We're talking about what the universe is all about. And we're talking about meteor showers, the Gemini meteor shower, which you can catch in the next few days. But Ken, isn't it also true that larger asteroids could pose a problem? Specifically, there's an asteroid called Apophis. It's supposed to whiz by the planet Earth in 2029 and come back for a second try around 2036, I understand. And there's some worry, not much now because we have better statistics now, but at one point people were worried that Apophis could actually strike the Earth. So Apophis, being 1,000 feet across, could do a considerable amount of damage, but smaller objects the size of a football field or smaller, could also create havoc. Look at what happened to Chelyabinsk in Russia just a few years ago. So isn't it true that we could still be caught off guard, that we don't track these smaller objects?
Yes. The problem with the smaller objects is not that we wouldn't like to track them. The problem is they're fainter and harder to see because they are smaller. We think we know about the rather larger things like the size of the asteroid that did in the dinosaurs some 66 million years ago. That asteroid was maybe 6, 7, 8 miles in diameter. The asteroid that produces the Geminid meteor shower, which we were talking about, the Arecibo radio telescope indicates is about 4 miles in diameter. So we know about asteroids of that size fairly well. But as you point out, the smaller ones, which would not lead to mass extinction if they hit the Earth, but would do some damage, are harder to track. And there are more of them because, in general, just in nature in general, the smaller things outnumber the big things. And there are more small asteroids than big ones. So we think we know all about the big asteroids. It is the smaller ones that can indeed catch us off guard just because they're so faint and hard to see.
And just a few days ago, an object about 20 feet across or so just went right by the planet Earth at a distance of one-fifth the distance from the Earth to the Moon. And we were clueless. We had absolutely no warning of this until it whizzed by the planet Earth. And, well, these things happen. So don't you think that at some point in the future we should launch satellites that could detect some of these smaller objects? Because even though they're smaller than a football field, that could still cause a lot of damage. An object the size of an apartment building would be enough to take out a city. So don't you think that we should spend some time tracking these things?
It definitely makes sense. Now, one way to view these small objects, by the way, is that they are leftovers from the formation of the planet Earth, right, and the other planets. So it was small objects coming together that formed the Earth. So we shouldn't be too distressed that there are these objects still out there. They are, in a way, a reminder that that's how Earth arose 4.6 billion years ago.
And speaking about debris in outer space, some people are applauding the fact that SpaceX, the pioneering organization led by Elon Musk, is going to launch maybe 1,000 mini satellites to bring the internet to everyone on the planet Earth. So even if you're in the middle of the ocean, even if you're in the middle of a deserted desert, you can access the internet compliments of SpaceX. But astronomers are not too happy because every time they take a photograph in outer space, who knows, maybe you're going to pick up the debris from one of these 1,000 satellites orbiting the Earth. And we just had another successful launch just a few days ago. So what's the consensus? What's the feeling among astronomers that maybe, just maybe, their photographs are going to be ruined by having up to 1,000 mini satellites blocking the view? What are your thoughts?
Well, the concern is that you will have these objects streaking through images that, for example, telescopes are taking to look for these asteroids that we would like to discover, and will be obstructing the view in that regard. So, yes, there is some concern among astronomers that these objects, being so numerous, could masquerade as celestial objects and basically interfere with our work.
Okay, Ken, let's take another short commercial break. Once again, you are listening to Science Fantastic. If you want to get on the air, then give us a call at 612-564-8135. Leave your name, call letters to the radio station or website you're listening to, and the city you're calling from, and bingo, maybe you can get on almost 100 radio stations that carry Science Fantastic.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again with us today is astronomer Ken Croswell, author of Alchemy of the Heavens and a number of other great books that I highly recommend. And we're talking about your backyard, the universe. You should look up and see the glorious universe that we live in. But astronomers complain. First, they complained about light pollution, the fact that telescopes around Los Angeles were more and more obscured by the fact that LA was lighting up like a Christmas tree and ruining some of their astronomical work. And now astronomers are complaining about the fact that SpaceX, the pioneering organization that wants to go to the moon and Mars and beyond, that SpaceX is going to launch 1,000 mini satellites in outer space to bring the internet to the average person in the middle of the ocean, in the middle of a desert. Yes, you will have internet access, but that means, again, hundreds, thousands of mini satellites obscuring the view of astronomers. So SpaceX, in response, said that it would try to perhaps change the reflective ability of these objects so they don't reflect so much, and perhaps put them in lower orbit around the Earth. But, well, has the astronomical community been assuaged by these measures that SpaceX will lower the altitude of these satellites and perhaps give them some absorptive ability to absorb starlight? What are your thoughts?
Well, it would certainly be nice. Simply painting them as black as possible would be fantastic, because then they'll be considerably fainter and will be less of a problem for astronomers. But yes, astronomers are definitely concerned about these things.
Okay, now also, if you scan the internet, there's been rumbling every now and then about a new planet X. Well, Pluto, of course, according to most astronomers, was kicked out of the solar system unceremoniously. So we have 9 planets going out to Neptune. But there's always been talk about a 10th planet, not Pluto size, but Neptune size, orbiting the Earth, orbiting the Sun beyond the planet of Neptune. And there was also a recent blip on the internet just last week stating that ancient conceptions of our early solar system billions of years ago showed that there could have been a planet, again the size of Neptune, between Neptune and Uranus that was hurled into outer space, leaving a gap. But what are your thoughts? What are your thoughts about the fact that maybe there is a planet X, a giant planet, not just like Pluto, and maybe there was an ancient planet X as well? What are your thoughts?
Well, various astronomers have thought that there might be a giant planet beyond the orbit of Neptune ever since the 1800s. Percival Lowell thought there was. Percival Lowell was best known for his work on Mars, but he, during his lifetime, led a search for a 9th planet. That search did not bear fruit during his life, but in 1930, Clyde Tombaugh, who worked at Lowell Observatory, discovered a new planet beyond the orbit of Neptune. However, that planet turned out not to be a giant planet, but a planet smaller than Earth, and that is the planet Pluto. The question is there still any good evidence for a large planet beyond the orbit of Neptune and the planet Pluto? And the answer there is not at all clear. During the 1980s, there were signs that the orbits of Uranus and Neptune were being perturbed by something. However, in the early 90s, an astronomer named Miles Standish reanalyzed the data and showed that it was actually incorrect knowledge of the mass of Neptune that led to these apparent irregularities. Neptune had received a spacecraft by the Voyager 2 spacecraft in 1989, and it gave us a much more precise mass estimate of Neptune. And when Miles Standish used the new mass from Neptune, the evidence for that giant planet beyond Uranus and Neptune went away. Now, more recent years, there has been additional evidence that maybe there is a giant planet out there, Planet X, but my attitude is, if you want to convince me that there really is a giant planet out there, you're going to have to find it and show me where it is. Because, as I say, astronomers have been suggesting this idea ever since the 1800s, and they have found no firm evidence for it. They haven't found any planet. Okay, so you need to find the planet. Now, in the early days of our solar system, it's certainly possible that the solar system had more than the 4 giant planets that we see today. The 4 giant planets are Jupiter, Saturn, Uranus, and Neptune. There could have been a 5th giant planet, perhaps comparable to the masses of Uranus and Neptune. But as those 4 and 5 planets actually interacted, one of them got flung away, maybe into a very wide orbit around the sun, or maybe kicked out of the solar system altogether. So it is possible there was a 5th giant planet, but of course, if it was kicked out of the solar system altogether, there's no way we're ever going to be able to find it.
And also bringing it closer to home, the moon. Recently, scientists were amazed to find that there is water on the moon, not just in small quantities, perhaps near the poles, but perhaps toward the center of the moon. But what are your thoughts about water being found on the moon? Is it ice water? Is it drinkable water? Is it water usable for astronauts? What about the recent statements that there is water on the moon?
Well, there probably is some water on the moon. Water is actually a very simple compound. It's simply hydrogen and oxygen. Hydrogen is the most common element in the universe. Oxygen is the 3rd most common element in the universe. And so H2O, water, exists in many places. For example, the rings of Saturn are made of water ice, and there is probably some water in the form of ice on the moon, especially in the polar region.
Okay. Unfortunately, Ken, we've run out of time. But, Ken, thank you so much once again for being on Science Fantastic.
You're very welcome.
And once again, Ken Croswell, astronomer at Berkeley, is the author of a number of great books, including Alchemy of the Heavens, and you are listening to Science Fantastic with Professor Michio Kaku. If you want to be part of the March of Science, then give us a call. 612-564-8135 is the number to call. Leave your name, call letters of the radio station or website, and the city you're calling from, and maybe you can have your thoughts heard on national radio. So once again, for Science Fantastic, this is Professor Michio Kaku at mkaku.org.
Professor Michio Kaku
and GCNlive.com.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. I'm a professor of theoretical physics at the City College and the Graduate Center of the City University of New York. And in this hour, we're going to throw the lines open because, hey, this is your hour. Are you sick and tired of simply listening to the TV and listening to the radio and not being able to interact with the host? Well, here is your chance to get even. Give us a call. The hotline number, write this down. The hotline number is 612-564-8135. Once again, it's 612-564-8135. You can also go to my website and ask the question directly off the website. Website is mkaku.org, mkaku.org. And again, leave your name, call letters of the radio station or website you're listening to, and the city you're calling from, and then ask away. Here's your chance. Here's your chance to ask that question that you've always been waiting to ask but never had the opportunity. You know, years ago, I was on a book tour, and a person came up to me after the lecture, and he says, "Professor, you have got to answer my question." And I said, "Well, gee, why? Why do I have to answer your question?" And he said, please, it's because if you don't answer my question, it will be another 10 years before a theoretical physicist comes by this town to answer this same question. And I thought to myself, and I said, he's right. I mean, how many theoretical physicists are there in the United States? There are not that many of us. For example, how many of us do string theory? Oh, about 100. That's it. Out of a population of almost 1/3 billion in this country, there are only about 100 of us that work on the unified field theory. Well, anyway, here is your chance to ask that question, no matter how complicated or obscure it is. Chances are, if you have that dumb question, chances are scores of other people have the identical same question, but are simply too embarrassed to ask. Well, you can ask that question on Science Fantastic, because sometimes the dumbest questions are the most profound questions of all. Years ago, there was a gentleman who was walking down a country road, and he saw the moon, and he saw an apple fall. And then he asked himself a stupid question, and that is, if an apple falls, does the moon also fall? He thought about it, and he said, yes, the moon is in free fall. It doesn't hit the Earth because, of course, it rotates around the Earth. But yeah, the moon is in free fall. In fact, almost everything is in free fall. Unless something is sitting on the floor or resting on something, yeah, everything is in free fall. Walking is free fall. This young man's name was Isaac Newton. And he initiated what we call the Industrial Revolution by writing down the laws of mechanics, the laws of rocket ships, the laws of gravity. A comet sailed over London around that time. Everyone was talking about the comet, including a man named Edmund Halley. He visited Isaac Newton and asked him, the comet, everyone is talking about the comet. What is it? And Isaac Newton said, oh, that's easy. It's moving in an elliptical orbit. I've been tracking it with my telescope that I recently invented, and it's undergoing an inverse square law. Well, you can imagine that Edmund Halley's jaw hit the floor. I mean, comets were a mystery, an object of superstitious worship. The king must die, people said, when a comet looms overhead. And here was this young man saying he's worked out the trajectory of comets. And they said, this comet is going to come back in 76 years, he predicted. And sure enough, on Christmas Day, 76 years later, when both Edmund Halley and Isaac Newton had passed away, a comet sailed over London, sealing the fame of Isaac Newton. And why was he so famous? In part because he asked himself a stupid question. Does the moon also fall? He created a mathematics to calculate the falling moon, and that mathematics is called calculus. Well, anyway, give us a call. All you have to do is call 612-564-8135. Leave your name, call letter to the radio station or website you're listening to, and the city you're calling from, and then ask that question. Okay, let's move on now and take the first listener phone call.
Hi, Dr. Kaku. My name is Jason Sorensen, and I follow you on Twitter. I'm calling from Los Angeles. The question that I have for you that's been on my mind, we talk about dark energy, and I'm trying to wrap my head around this concept. As we look further out into the universe, we see that galaxies are redshifting faster and faster away from us. But as we look further out into the universe, we're also looking further back in time. So doesn't that mean that the expansion of the universe is actually slowing down? Because as we get closer and closer, it's less and less time dilation. Whereas the further out we look, the further back in time we're looking. So just trying to get my head wrapped around dark energy, and hopefully this question makes sense. Thanks.
Okay, well, your question makes sense because it goes to one of the great unsolved problems in all of physics. It goes back to a question asked 2,000 years ago by the Greeks, and that question is, what is the world made of? Well, we used to think for 2,000 years that the universe was made mainly of atoms. Well, that's not true. We now realize that about 4% of the matter energy of the universe is in the form of atoms, that 23% is in the form of dark matter, which is invisible matter, which holds the galaxies together, And 73% is in the form of dark energy, which is what you mentioned. Dark energy is the energy of nothing. It's the energy of the vacuum, which is pushing the galaxies apart. Now, it was Nikola Tesla, who the father of modern electronics, along with Thomas Edison. It was Nikola Tesla who said that it's possible to extract energy from nothing. Well, not quite true, but he was close. Energy from empty space. It turns out that Einstein's equations contain a term called the cosmological constant, which shows that even nothingness has energy associated with it. And this energy is repulsive. It is very faint, but it is sufficient to push the galaxies apart, and that gives us the expanding universe. Therefore, if a yellow star is moving away from us, light is stretched as it comes to the Earth. And when you stretch yellow light, what happens to yellow light? It turns red. And that's called the red shift. And when we look in the heavens, we see that almost uniformly, all the galaxies, except for a few, are moving away from us. This is called the red shift. And we think that what is driving it is dark energy. Now, the question is, how do you predict how much dark energy there is? If you get a sheet of paper and you do the calculation as to what you think dark energy should be, you come up with a number which is off by 10 to the 120. That is 10 raised to the 120 powers. That is 1 with 120 zeros after it. This is the greatest embarrassment in all of physics. We're clueless as to why dark energy is off by 10 to the 120. Well, let's take a short commercial break. And if you figure this out, by the way, be sure to tell me first, and we'll split the Nobel Prize money together. And give us a call at 612-564-8135.
Brought to you by Professor Michio Kaku. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. You're not going to get a busy signal. All you have to do is call 612-564-8135. You'll get a recording. Leave your name, call letters to the radio station or website you're listening to, and the city you're calling from, and then ask that question. Make that comment that's always been bothering you. Why should science be a secret? No. You can be part of the March of Science by giving us a call and leaving your name, call letters to the radio station or website, and the city you're calling from. Okay, let's move on now to the next listener phone call.
My name is Harry. I'm calling from Rochester, New York area. I'm listening out of WGVA. And my question is, I want to hear something about harvesting helium from the moon. About a year ago, I was listening to some program, I don't know, but they were talking about going to the moon, and just a few inches under the moon is tons of raw material of He2 and tons of helium, and that one payload of a space shuttle will actually produce enough non-pollutant energy for the United States for an entire year. So, do you know anything about that? Thanks again.
Well, yes, I'm quite familiar with the calculation you mentioned, but I think the people who made that statement are kind of overstepping what is known. Let's back up. When we go to the moon, people want to know, can we mine the moon? Can we get materials that'll pay for going to the moon? Well, for the most part, the answer is no. It turns out that we know what the moon is made of. The moon was basically blasted out of the Earth about 4 billion years ago. And as a consequence, the chemical composition of the moon is almost identical to that of the Earth. So if you were to mine ores on the moon, it's very expensive. You can simply mine ores in your backyard. You don't have to go to the moon. However, some people think that helium-3 is rare on the Earth and is slightly more plentiful on the Moon and could be used in fusion reactors to generate power. Now, great. Hey, I'm all for that. But what's the catch? There's always a catch someplace. The catch is, first of all, fusion reactors don't exist. In fact, we're not even sure they work. In southern France, in Cardache, France, the European Union is basically backing the ITER fusion reactor, the most advanced $10 billion machine on the planet Earth. But unfortunately, it has been delayed once again. The joke is that every 20 years, we physicists claim that we'll have fusion in 20 years. 20 years after that, we make the next claim, give us another 20 years. Well, it's been pushed back again. Now, personally, I think this is the way to go. Personally, I think that one day we will get fusion reactors on the Earth and gradually wean ourselves away from fossil fuels. But that time is not now. And helium-3 requires a fusion process that's even more exotic than the ones being explored by the ITER. So what's the catch? The catch is, first of all, A, we don't really know how much helium-3 the Moon has. And B, even if we do find helium-3 on the Moon, it may take decades until we finally have a fusion reactor on the Earth which can burn helium-3. Now, most people on the Earth think that seawater is perhaps an easier fuel to get rather than getting helium-3 from the Moon. Seawater contains helium, ordinary helium, hydrogen, and you can fuse hydrogen from seawater to extract energy. So why am I for space travel? Well, as I said before, the economics of mining the Moon are iffy. The economics of mining asteroids, however, is possibly a better shot because asteroids have platinum and rare earth elements that are valuable that are not necessarily found plentifully on the planet Earth. You see, when the Earth was molten, many of the heavy elements sunk toward the center of the Earth like platinum-based materials. In outer space, the asteroids did not go through that process. The asteroids did not come from a planet that was molten where gravity slowly sucked in the heavy elements. As a consequence, exotic elements are more common in asteroids than the Moon. The Moon, on the other hand, was blasted out of the Earth about 4 billion years ago. An object about the size of Mars plowed into the Earth and blew out enormous chunk of Earth into space, which eventually coalesced because of gravity into the Moon. So once again, yes, you can argue that helium-3 is a goal for the space program, but B, we don't know how much there really is. And most important, we don't have a fusion reactor to burn helium-3. Okay, let's move on now to the next listener phone call.
This is David from Central Lake, Michigan, WMKT. I'd like you to do a discussion of the limits in the universe. We supposedly know the limits of the speed of light. I would ask whether light speeds up if it's a light beam is heading straight into a black hole. Temperature, we understand there's a limit to the low end of the temperature scale, but is there a limit to the high end of it? Is there a limit to the density? We know that if the Big Bang is true, then obviously the black hole reached its limits and exploded. Is there a limit to the number of elements? Is there a limit to the actual space? If the universe is expanding, what is it expanding into, and is there any end to where we can expand into? Is there a limit on the amount of dimensions that is possible? Well, just generally, I'd like you to discuss the limits of physics. Thank you.
Wow, you asked about 10 questions in one. The basic question being, what is the maximum of anything? The maximum temperature, the maximum weight, the maximum density. Is there an upper limit to these parameters? Lower limits, of course, exist. We have, hypothetically, absolute zero, the lowest temperature you can get. So let's say a few things about that. First of all, the maximum temperature. The hottest temperature we see in the universe comes out of collisions of black holes. However, the question is, can you get bigger and bigger black holes? And the answer seems to be yes. There's no limit to how much mass you can concentrate in a black hole. The black hole M87, which hit the newspapers, that black hole weighs 6.5 billion times the mass of the sun. It basically outweighs a galaxy. One small black hole at the center of the galaxy M87 weighs as much as 6.5 billion suns. Is there an upper limit to this? And for the most part, we see no upper limit. Is there an upper limit to density? Well, if I take the sun, for example, and I were to squeeze the sun, eventually it would become a white dwarf. And eventually the white dwarf would decay into a black dwarf and drift as a piece of nuclear waste. But if you could somehow squeeze that, which is not going to happen, our sun will not turn into a black hole. But if you could squeeze the sun down to about 2 miles across, assuming you could squeeze the sun down to a sphere 2 miles across, it will implode and become a black hole. And so is there a limit to the density of a black hole? And apparently not. You can simply dump more and more materials into a black hole. And then is there the farthest star? Is there a limit to how far you can see with a telescope? Well, actually there is a limit here. It turns out that the Hubble Space Telescope, peering into outer space, looks into the past, because light takes time to reach your eyeball, and therefore you've probably seen pictures of it. The farthest galaxy that you could see with a telescope, and then what is beyond the farthest galaxy? Blackness. There is a limit there because you're going backwards in time. So what is this blackness that lies beyond the farthest star? It is the Big Bang itself. Since the Big Bang did not take place mainly in the optical region, but in the microwave region, that's why it's black. You're basically looking at Genesis itself. The farthest star is actually the creation of the universe. Okay, let's take a short commercial break, and after that we're going to continue with Science Fantastic. Give us a call at 612-564-8135. Welcome back to Science Fantastic with Professor Michio Kaku. Keep the calls coming. The hotline number, if you want to get on air, is 612-564-8135. And also go to my website. It's mkaku.org, mkaku.org. On Facebook, we have 3 million fans on Facebook. On Twitter, we get about 1 million people that pick up the Twitter feeds. So find out what the fun is all about. Also, I've written 4 New York Times bestsellers. In my book, Physics of the Impossible, I talk about the impossible and whether or not one day we'll have time machines, teleportation, invisibility, starships. In the future of the mind, I talk about how physics is teasing apart the secrets of thinking itself, telepathy, telekinesis, recording dreams. We can do it in the laboratory because of physics, believe it or not. And in Physics of the Future, I talk about the next 100 years. The next 100 years in the job market, cancer research, longevity, transportation, artificial intelligence. And my latest book is The Future of Humanity, Our Destiny in Outer Space. One day will we colonize Mars. Will we go beyond that, leave the solar system, and build our first starship? Once we do that, what happens if we encounter intelligent life in outer space, which is also expanding into the unknown? So go to my website, mkaku.org. Okay, let's move on now to the next listener phone call.
Hi, Dr. Kaku. My name is Jay, and I'm calling from New York City. I'm listening to your broadcast through the Internet. Anyway, I've read several of your books, and I've really enjoyed them. I think your writing is very clear and speaks perfectly to the audience. I love that. My question involves quantum entanglement, and I'm wondering if you think someday that it could be used for communications. For example, I believe it takes like 20 minutes now to get a communication to the rover between Earth and Mars. But if quantum entanglement could be used, that 20 minutes could be eliminated. It would be virtually instantaneous. And I appreciate your work. Bye-bye.
Well, if you're a Star Trek fan, you know that the Captain Kirk can talk to Federation headquarters instantly, faster than the speed of light, by using something called subspace communications. Communication through subspace. Now, what is that? Maybe it's quantum entanglement. However, there are problems there. Personally, I think that one way to really communicate faster than the speed of light is through a wormhole. But again, to harness the energy of a wormhole, you have to be able to harness the energy of a black hole, which is very difficult. But let's talk about quantum entanglement. If I have two electrons are vibrating, and let's say you make them touch and they vibrate together in unison. Then you separate them. When you separate them, an invisible umbilical cord emerges connecting these two electrons, such that if you jiggle one electron, then the other electron, faster than the speed of light, is aware of the fact that its partner is being jiggled. So, for example, let's say I have two electrons, one spinning up, one spinning down, like a top. When I separate them, and I measure the spin of the first electron, it is spinning up. Then what is the spin of the second electron? Down. And that information travels faster than the speed of light. Well, there's a catch there. Let's take a short commercial break, and after the break, I'll talk about the catch involved with quantum entanglement. If we could do it, we could talk faster than the speed of light. Okay, once again, you're listening to Science Fantastic. Give us a call. Science Fantastic with Professor Michio Kaku. On Science Fantastic, we take your questions, any and all questions about the cutting edge of science. And here's your chance to get on national radio to share your thoughts. Before the break, we had a question about quantum entanglement. To talk to a person on Mars takes about 20 minutes. If you have somebody on Pluto, it would take you 8 hours to a day to send a message to Pluto. To send a message to the nearby stars would take 4 years minimum. And so is there a way to communicate faster than the speed of light? Well, one possibility is wormholes, but that requires a fantastic amount of energy. Another possibility is quantum entanglement. Einstein was wrong on this one. Einstein said that nothing can go faster than the speed of light. Information from one electron to the other cannot travel faster than the speed of light, but quantum entanglement has been measured. We've done this in the laboratory, and bingo, if you jiggle one electron, its partner feels the effect of that jiggling faster than the speed of light. On this question, Einstein was wrong. We know that because we can duplicate this in the laboratory. So you may say to yourself, well, if that's so great, how come we don't have subspace communicators? Why can't we communicate with our space probes faster than the speed of light? Well, there's a catch. There's always a catch someplace. That catch is that, yes, some form of information traveled between one electron to the electron faster than the speed of light. The problem is that information was random. It was chaotic. It was useless. Now, Morse code, on the other hand, is not useless. When you send Morse code, each code corresponds to a letter. Letters correspond to words. Words correspond to concepts. That means you can send net information on Morse code. However, when you send information with quantum entanglement, what do you get? You get gibberish. So it's not useful. So at the present time, the only known way of possibly communicating faster than the speed of light is through a wormhole, which requires vast amounts of energy, stellar energy. But quantum entanglement, well, we can do it in the laboratory. We can send information faster than light, but it is useless information. Sorry about that. Okay, let's move on to the next listener phone call.
My name is Malcolm McLean. I'm in the Finger Lakes area of New York. It's 1240 WBBA. And the question is, I thought a few years ago at Brookhaven, they were attempting to do an experiment where they would generate a minuscule black hole. And, of course, everybody was worried if we did something like that, could we generate a black hole that would run away? Okay, thank you.
Okay, well, I think I am partially responsible for the incorrectness of that idea. Years ago, I was talking to a producer at the Science Fiction Channel, and I mentioned, that we're building this accelerator in Geneva, Switzerland, the Large Hadron Collider, and some people think that maybe there could be a runaway reaction, maybe a black hole could be created in that machine. And then I was careful to say that it's not going to happen. Well, the producer from the Science Fiction Channel, his eyes lit up, and sure enough, without my permission or whatever, he ran with the idea and did a program where an accelerator created a black hole with all sorts of monstrous effects. Well, the idea is out there. If you saw the latest Spider-Man cartoon about entering the Spider-Verse, you realize that the whole Spider-Verse of parallel universe Spider-Man was unleashed by a particle accelerator. Well, first of all, let me set the story straight. To create a wormhole, you need the energy of a black hole. And a black hole would require the energy of a star. We are nowhere near being able to create the energy of a star with the Large Hadron Collider. Second, even if you could do that, in outer space, we see cosmic rays. Cosmic rays with more energy than can be created with our puny pea shooters called the Large Hadron Collider. And hey, we're still here. The fact that we are still here is proof enough that there's no danger from a Large Hadron Collider. Well, let's take a short commercial break, and after the break, we're going to continue with your phone calls. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. That's right. This is your chance to ask that question or make that comment that's always been bothering you, but you just never had that opportunity. Well, here's your chance. You can call us at 612-564-8135. So why don't you become part of the March of Science? Why should we scientists have all the fun teasing apart the nature of reality itself? So give us a call at 612-564-8135. Anything is fair game. We're talking about stars, galaxies, astronomy. We're talking about health, cancer research, biotechnology. We're talking about dinosaurs. We're talking about ancient civilizations. We're talking about future civilizations. We're talking about life in the future. All these topics are fair game if you call 612-564-8135. Okay, moving on. Let's take the next listener phone call.
Hi, Dr. Michio Kaku. I'm Vincent Mishi, and I'm calling from New London, Minnesota. It's easy to understand that there are 3 spatial dimensions, and this 4th singular dimension of time. Gravity is bestowed by Higgs boson particle in a sense, and then it gives mass. That's my understanding right now. I'm interested if there was some small quantum particle that would denote time, the passage of time. If this is true, would time be unique to each individual particle? Would they each have their own unique time? Similar, but different. I'm wondering what your thoughts are about that, Doctor. Thank you.
Okay, well, you ask a question about the nature of reality itself. And, well, we have Einstein's theory, which gives us the most advanced understanding of space and time. First of all, you ask whether or not each particle has a clock associated with it. Well, there is one version of quantum mechanics where you can do that. However, it's not necessary. That is, time is everywhere. It's a parameter by which we measure the entire universe. However, you could put a clock on a subatomic particle. That's called proper time. And yes, there is a formulation of quantum mechanics where there is a clock on each particle as it moves in space and time. But does it have a physical significance? Well, not that we know of. We think that it's a way to parameterize space and time. Now, Einstein says that space and time are not really different. That if I move at a certain velocity, I can rotate space into time and time into space. And so time no longer has an individual meaning. That is, space can be interchanged with time simply by moving in a straight line. And then he wrote down, of course, his famous equations which make this possible. At first, people thought, wow, this is nonsense. Time turns into space. Space turns into time. But yeah, not only that, but matter turns into energy. Energy turns into matter. So not just space and time, but matter and energy also turn into each other. And the simplest consequence of that is the atomic bomb. The atomic bomb is a consequence of the fact that time can turn into space, space can turn into time, which forces matter to turn into energy, and energy to turn into matter. So that a rock, like uranium, can be turned into energy in the form of a nuclear fireball through Einstein's equations. Okay, let's move on now to the next listener phone call.
Dr. Kaku, this is Ben Stanton from Dallas, Texas. I'm calling because I saw your Twitter post. I read The Future of Physics in 2012, and it was very encouraging. My question to you is there any evidence in our reality that the Earth ever had exactly 360-day rotations around the sun? If so, why do we now have 365-day rotations if that is possible? Is it possible for the Earth to have different rotations around the sun than we do now and it still be habitable? Thank you very much for your time, and wish you all the luck. God bless.
Well, that's a very interesting question because, first of all, we have Newton's laws of gravity, which allows us to calculate the trajectory of the Earth. But now we have supercomputers. Supercomputers which allow us to hit the fast forward button or the rewind button to go back millions, billions of years into the past. And that opens up a whole new realm of astronomy, because we're not used to thinking of the solar system billions of years ago. For example, the moon came out of the Earth about 4 billion years ago, and it was much closer to the Earth. And so a day on the Earth was different than a day back then. Same thing with a year. So we know that a year is 365 days, but that was not always true. And in fact, 4 billion years ago, an object about the size of Mars plowed into the Earth, gouged out a huge chunk of the Earth, which then solidified under gravity, and it became the moon. So we know, therefore, that what we see today was not the way it was, and in the future, it may not be the way it will be in the future. Now, you ask whether or not life can even exist in a situation where the parameters of the day and night are shifted. And for that, well, if the moon were to disappear, the Earth would wobble in its orbit over billions of years, and the Earth would tumble, and life would become impossible. And so the answer to your question is, there are scenarios where life itself become impossible if you change the parameters of the Earth, so that the Earth tumbles because we are missing the moon. Okay, well, that's it for Science Fantastic. And again, give us a call at 612-564-8135. Go to my website, mkaku.org, and find out what I've been up to. I've written 4 New York Times bestsellers, and we also have about 3 million fans on Facebook, and about 1 million people pick up my Twitter feeds every week.
Black holes, the cosmos, space, and time travel. science, and technology. Brought to you by theoretical physicist, futurist, popularizer of science, and world-renowned author, Professor Michio Kaku.
At GCNlive.com.
This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And also, be sure to drop in on my website. It's mkaku.org, mkaku.org. And it lists the 4 New York Times bestsellers that I've written. My latest one is The Future of Humanity, talking about the future of the space race, the future of Mars exploration, what happens when one day we go beyond the solar system to the nearby stars. And in my other New York Times bestseller, The Future of the Mind, I talk about how physics is beginning to probe the secrets of the living brain. Things that were once considered preposterous in science fiction, like telepathy, telekinesis, mind reading, or things that we see in the movies we can actually do in the laboratory, like recording dreams. These are things that were once considered beyond the pale, and now we can do in the laboratory. And so once again, the website is mkaku.org, mkaku.org. And also on Facebook, we have 3 million fans on Facebook and over 600,000 fans on Twitter. And in this hour, we're going to throw the lines open because it's open mic on Science Fantastic. You're not going to get a busy signal if you call 612-564-8135. You'll get a recording. Leave your name, call letters of the radio station you're listening to, if you're listening to radio, and the city you're calling from, and then make that comment, ask that question, and maybe you can get on national radio. So in other words, give us a call, 612-564-8135, and ask that question, make that comment, and perhaps your thoughts will be heard across the country on national radio. And just remember that some people say, well, gee, maybe I'm not smart enough, or maybe my questions are too dumb. Just remember, if you have a question, chances are thousands of other people have exactly that same so-called dumb question. And sometimes the dumb questions are the most profound questions of all. Science starts with that dumb question. That's why we have so many advances in science, precisely because people ask those dumb questions. So once again, give us a call, 612-564-8135 is the number to call. Okay, well, let's just jump right into the first listener phone call.
Hello, my name is Krish from Cupertino, California. My question relates to reactionless propulsion. And when I say reactionless, I do not mean any false impressions like electromagnetic levitation, centrifugal force, or anti-gravity, etc. Today, if I tell anyone about a concept for reactionless propulsion, everyone suggests me to first develop a theory which would be hundreds of times harder than just conducting the experiment and finding it out. On the other hand, whenever we enabled frictionless motion, invention of wheel, the actual theory was followed thousands of years later. Why is this contrast? Has the theoretical advancement become a barrier to non-incremental experimentation? Especially because current theories, which by the way are great for incremental stuff, but we do not know whether they will even turn out to be consistent with the reactionless propulsion or not. Your thoughts, please. Thank you.
Okay, well, first of all, I'll give you a reaction to your question about a reactionless propulsion, and then I'll give you some advice about what to do with your theory. First of all, we have Newton's 3 laws of motion, and reactionless propulsion would violate the third law. let's go through the 3 laws very simply. The first law of motion, if you go ice skating, and that is an object in motion, stays in motion unless acted on by an outside force. So if I have an ice puck, for example, and I throw it on an ice rink, it seems to go on forever. In fact, it will go on forever if it wasn't for friction, which is an outside force. So in outer space, if you are in motion in outer space, in principle, you go forever without stopping. And that's how our space probes can go all the way out to Pluto and beyond. They coast. They coast once they're in outer space. They don't need rocket fuel. They don't need large amounts of gasoline to reach Pluto. No, they simply coast because there's no friction in outer space. The second law of Newton is force is equal to mass times acceleration. That gives us equations by which we can calculate the tensions on a bridge, the tensions in a rocket ship, and the tensions in the Empire State Building. When I was a kid growing up in California, I used to hear about the Empire State Building, and I used to wonder, how can they build the Empire State Building without knowing ahead of time if it's going to fall down? I mean, you can't make a model, right, of the Empire State Building that's realistic. So how do they know it's not going to fall down? Well, the answer is we have Newton's second law of motion, and that allows you to calculate the stresses on every single brick inside the Empire State Building. In fact, now that I teach physics, I actually give students problems like that, calculate the tensions inside a bridge. Next, we have Newton's third law of motion, which deals with reaction. The third law of motion is known to every child who's ever blown up a balloon. When you release the air on the balloon goes shooting out in the opposite direction. So air goes in one way out the nozzle, and the balloon goes the other direction. That is action-reaction. Now, what this listener proposes is a reactionless propulsion. That is, propulsion like a rocket ship without the rocket, that is, without the exhaust. Now, that'd be great. For example, if I have a reactionless propulsion for a gun, I can shoot the gun and not feel the recoil. But if you ever fired a gun, and I fired many guns because I was in the United States military for about 2 years, when I fired machine guns when I was in the military, I realized that there was a back reaction on my shoulder. And therefore, you have to sort of grit your teeth, knowing that when you fire a machine gun, you're going to get that rapid fire reaction on your shoulder, which could actually hurt. Now, same thing with rockets. If you have a reactionless propulsion system, it means you can have the rocket without the fuel. In other words, it would take off pretty much all by itself because you need the fuel for action, and then the reaction is motion in the forward direction. Well, so far we see no violation of Newton's third law of motion. We have skyscrapers, rockets, bulldozers, buildings. At no point do we see a violation of Newton's third law of motion. That's why some people think that the search for a reactionless propulsion is futile. Now, let's say you have a theory. Then what are you going to do about it? Some people are hesitant to publish that theory because then your rivals will scoop you and steal your invention. Well, what you ought to do is several things. One, get a patent. In fact, you may want to consult with a patent attorney to get that patent. However, many patent officers require a model that works. Well, let me take a short commercial break, and after that break, I'll give you a word of advice if you have a great invention and you want to make sure that no one steals your idea. Once again, give us a call. 612-564-8135 is the number to call if you want to get on Science Fantastic. Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. If you want to ask a question, make a comment, give us a call at 612-564-8135. When you hear the recording, leave your name, call letter to the radio station you're listening to, if you're listening to one, and the city you're calling from, and then ask that question. Make that comment right to the tape, and maybe your thoughts will be heard on national radio. Well, before the break, we had a question about reactionless propulsion. Many people have tried to create that, because then you could basically have motion without the rocket fuel. Think about that. Rockets without rocket fuel. However, Newton's has the last word. For every action, there's a reaction. And we know that because we've tested it on rockets, airplanes, we've tested it on bulldozers, skyscrapers. Every time there's an action, there is a reaction. And that's codified in something called the conservation of momentum. So, sorry about that. If you are an inventor, I would suggest you try to invent something else other than something that violates Newton's third law of motion. However, if you do have a theory, what are the steps that you should pursue? Well, first of all, you may want to take a patent out on it. However, I warn you that if you have a patent for a perpetual motion machine, usually they ask for a demonstration model. So many people over the centuries have claimed to have created a perpetual motion machine. Energy from nothing. In fact, in antiquity, going back thousands of years, enterprising inventors would go to the king and claim that they can get energy for free. Usually it was some kind of spinning wheel of some sort. And of course, because of friction, you basically lose energy and have to add energy from the outside. But anyway, over thousands of years, people have tried to get inventions sponsored by the king, in which case they could become millionaires in the process. However, after centuries of analyzing all these perpetual motion machines, we physicists have come to the conclusion that there's something called the conservation of energy, which in turn is a byproduct of Newton's laws of motion. So in other words, the patent office will ask you for a demonstration model. Don't just think you can create something in the laboratory and become an instant millionaire. However, I do suggest that if you do have an idea, patent it. Talk to a patent attorney. Or if you simply want recognition for your idea and not necessarily to commercialize it, publish it in a magazine. There's several magazines you can submit it to. There's Physical Review, which is the magazine of my organization, the American Physical Society. It is the premier American physics magazine, Physical Review. There's also a European magazine, Nuclear Physics, for example, published by Elsevier Publishers in Europe. They are one of the leading publishers of nuclear information papers in the nuclear field. So if you have an idea and you don't want to patent it, but you want recognition for that theory, then you may want to send it to these magazines, and then you will get a referee. Sometimes more than one referee. In fact, I referee other people's papers all the time. Magazines send me articles to referee for their magazine. In fact, just last week, I got an article that a magazine wanted me to referee an article about astronautics of interstellar space travel. So those are the paths you can take if you have an idea and you don't want someone else to steal that idea. By the way, don't take it personally. Sometimes the referees can be brutal, but they'll be honest with you. The referee will tell you honestly why they think your idea is great or why it's a bunch of nonsense. Okay, let's move on now to the next listener phone call.
So you know how you can lucid dream? Oh, this is Armand again from Queens. Listening on YouTube. So you know how you lucid dream? I was wondering, if there's one day you can complete technology to make you able to control your dreams while you're sleeping, so you can actually function on in a virtual world while you're sleeping, while you're getting like a good night deep sleep. All right, thank you very much for that, and I love your show, and have a great day. Bye.
Okay, good. Well, just a few years ago, if you were to ask a question to a scientist about lucid dreaming, they would have considered you to be a crackpot. Well, not anymore. Lucid dreaming, that is the idea that you can control the progress of a dream, is actually correct. There are lucid dreamers who've been subjected to an MRI scan. When they fall asleep inside an MRI machine that analyzes blood flow. It turns out that when you dream, the blood to the prefrontal cortex, which is the thinking part of your brain behind your forehead, shuts down. That's why your dreams become fantastic. They violate all the laws of logic, not just the laws of physics. They violate the laws of logic because the front part of your brain is drained of blood when you dream. And then MRI scans show that the center part of your brain, that is the amygdala, lights up like a Christmas tree. And that's the seat of nightmares, the seat of emotions, the amygdala. And that's one reason why many of your dreams are nightmarish. So it turns out that people who are lucid dreamers have an active prefrontal cortex while the amygdala lights up. Both areas of the brain light up. So in other words, it's true. Not only that, but when you dream, you are paralyzed. So how do you talk to someone who's a lucid dreamer? You give them a piece of electrode in their hand, and you ask them to squeeze it. Even though they are paralyzed when they dream, they have the ability to squeeze gently an electrode in their hand. And that's how you can communicate. That's how you can actually talk to someone who's dreaming and communicate with them. And they can communicate with you by squeezing this electrode. This has actually been done now at the Max Planck Institute in Leipzig, Germany. They put a German who claimed to be a lucid dreamer inside the machine, and bingo, the prefrontal cortex was fully lit up even as he was in REM dreaming state. So in other words, lucid dreaming is scientifically possible. Then the next question is, how do you become a lucid dreamer? It turns out that Buddhist texts going back centuries have given people lessons as to how to become a lucid dreamer so that you can control the direction of your dreams. You can Google it. Some of these things are common sense. One is that just before you go to bed, you have a notebook. You see, when you wake up, right after a dream, you forget the dream within a matter of seconds. Within a matter of seconds, the memory of that dream simply disappears forever. So have a notebook. Write down the dream. Get in the habit of writing down the dream as soon as you have it, as soon as you wake up. Second, prime yourself. That is, before going to bed, say to yourself, I'm going to be a lucid dreamer tonight. I'm going to be awake. I'm going to control the direction of my dream. So get in that frame of mind that you are going to control the direction of your dream when you dream that night. Now, of course, we can't guarantee that you're going to become a lucid dreamer. However, the lessons are centuries old as to how to control the direction of your dreams. This is not science fiction anymore. We actually can do it now in the laboratory. Okay, let's move on to the next listener phone call.
Hi, Dr. Kaku. My name is Tim. I'm calling you from Dallas, Texas. My question regards dark matter. Is dark matter just matter that we cannot observe via visible light, or is it just something nebulous and unknown in the universe? I know that it makes up so much of the universe, and we don't know very much about it. So your thoughts on the matter would be very well appreciated. Thank you very much.
Okay, good question. Well, every high school textbook has to be rewritten. All the high school textbooks say that the universe is basically made out of atoms, but that's not true anymore. We know that there's something called dark matter, which outweighs ordinary matter by a factor of maybe up to 10. Now, how do we know that? First of all, the galaxy, the Milky Way galaxy, well, unfortunately, I have to take a short commercial break, but after the break, we're going to talk about dark matter. How do we know it exists? How do we have maps of dark matter? And what is it anyway? And why is it important? Once again, you are listening to Science Fantastic. Give us a call at 612-564-8135 and ask your question. Make that comment about science.
Brought to you by Professor Michio Kaku. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open because this is Open Mic on Science Fantastic. How many times have you watched the TV or listened to the radio or read the newspaper and something hits you? Something about the space program, something about the mind, something about human evolution, about medicine, and you are stumped and there's no one to talk to. Well, you can talk to me. You can give me a call at 612-564-8135. You know, I was on a book tour years ago, and a guy comes up to me once after my talk, and he says, you have to answer my question. You just have to answer my question. And I said to him, well, that's very nice. I'll answer your question, but why do I have to answer your question? And then he said, because if you don't answer my question, I may have to wait another 10, 20 years before another theoretical physicist comes by and can answer this question. And I was taken aback. And I thought to myself, and I said, he's right. You know, there are very few theoretical physicists in this world. And how many of them are going to be passing through this small town, signing copies of his book, answering detailed questions about string theory, about Einstein's theory of general relativity, about the unified field theory? So anyway, the point here is, if you want to ask a question, give us a call at 612-564-8135. You get a recording. Leave your name, call letters to the radio station, and the city you're calling from, and then ask that question. Make that comment, and perhaps you can get on national radio. Okay, let's move on now to the next listener. Oh, by the way, I forgot. I have to answer the question about dark matter before we move on. Dark matter was first found by astronomers decades ago, but it was dismissed because it was too preposterous. For example, the Milky Way galaxy spins. It looks like a pinwheel, in fact, but it spins 10 times too fast. By rights, it should fly apart. In which case the Earth should have been flung into outer space billions of years ago. But the Milky Way galaxy is quite stable, and we see these galaxies everywhere in the universe that are very stable, but all of them are spinning about 10 times too fast. Either this means that Newton was wrong, and we are very reluctant to give on Newton's laws of gravity. Either Newton was wrong, or there's a new form of matter in a halo surrounding the galaxy, keeping the galaxy intact, preventing it from flying apart. That's dark matter. Now we have maps of dark matter. Dark matter is invisible because when you photograph these galaxies, we don't see a halo around these galaxies at all. We just see a pinwheel. But they're stable, and they spin 10 times too fast, and we now have maps of dark matter. When light goes through glass, it bends light. So how do you know that there's glass inside your glasses? Well, glass is invisible. So how do you know that there's glass inside your glasses? Because light bends when it goes through your glass, and that's why you have eyeglasses. Same thing with dark matter. When light goes through this invisible matter, it bends. Then, using a computer, we can calculate how much dark matter there is by calculating how much bending of light there is. And you can Google it. You can actually see maps of dark matter reconstructed using computers looking at the bending of starlight. Well, let's take a short break, and afterwards we'll talk about what is dark matter anyway, and why should you care? Once again, this is Science Fantastic. Give us a call, 612-564-8135, and ask that question that you've always wanted to ask on national radio. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question about something that is requiring us to rewrite all the high school textbooks, and that is the presence of dark matter. What is it, and why should we care? Well, first of all, as we mentioned before, we have maps of dark matter which surrounds the Milky Way galaxy, holding the galaxy together so that it doesn't fly apart. And the next question is, what is dark matter made of? Well, the short answer is we don't know. There's a Nobel Prize waiting for that person who could finally tell us what dark matter is. However, there are many theories. The leading theory is that it's a new particle. We call it the photino, a particle that is the companion to the photon, which is a particle of light. The photino is invisible, is predicted by a theory called string theory, which is what I do for a living, and it is plentiful and invisible, but has mass. These are exactly the characteristics you want dark matter to have. You want it to have gravity, so it holds the galaxy together. You want it to be invisible, because we don't see anything with our telescopes when we look for that halo surrounding the galaxy. And this particle is predicted by string theory. String theory has not been proven, but it simply says that all matter consists of vibrations. Vibrations of a tiny rubber band. When the rubber band vibrates in different frequencies, you get different subatomic particles. Now, why don't scientists all uniformly agree with string theory? It's a controversial theory. Among other things, it states that the universe is not three-dimensional at all. We think that everything is three-dimensional. You can describe everything by its length, width, and height. However, string theory says that there are 11 dimensions, that our universe is a bubble floating in a much larger hyperspace universe. That's controversial. That's why some people don't like string theory at all, because it forces you to confront a many worlds. The idea that our universe is not just one bubble that's expanding, an idea given to us by Einstein, but there could be many bubbles out there, a multiverse of universes. Now, there is another way to explain dark matter, and that is, if there are these other universes, then matter can exist, stars can exist in these other universes. If these two universes are close together, we would feel the effect of gravity from this other universe, but it would be invisible, because light can only move in our bubble. Therefore, if you hover in hyperspace, you are invisible, but you exert gravity. But that's exactly what dark matter is. It's invisible, but exerts gravity. Now, that is a pretty wild theory, a theory that we are very close to a parallel universe where there are parallel galaxies out there, and that's what causes the halo. Well, personally, I believe in the first theory, that is, for the photino, that is the particle of the photon, is the origin of dark matter. And why should we care? Well, first of all, we are here today because of dark matter. If it wasn't for dark matter, the galaxy would have been split apart, would have been flung apart billions of years ago. And if it does turn out that dark matter is consisted of these higher resonances of the string, it'll prove one of the greatest theories of all time. That string theory is, in fact, the theory of everything. The theory that explains the entire universe. The fabled unified field theory, the theory of everything. But that's another story. Okay, let's move on now to the next listener phone call.
Hello, sir. This is Bear, spelled B-A-I-R, Bear Kloss. I found your question on Twitter, and I'm from Medford, Massachusetts. And my science question is, in this universe, is a black hole the other side of the Big Bang in a different universe? Thanks.
Well, at first your idea sounds ridiculous and preposterous, but actually there are physicists, colleagues of mine, who actually published papers in this idea. And this idea is very simple, and that is, if we have black holes, why can't we have white holes? In fact, Stephen Hawking wrote papers on this, the fact that somewhere in the universe there should be the opposite of a black hole, which is a white hole. A white hole, instead of absorbing matter, actually excretes matter, shoots matter out. And then the question is a white hole on the other side of a black hole? Well, we'll talk about that after the break. Once again, you are listening to Science Fantastic with Professor Michio Kaku. Give us a call at 612-564-8135. Welcome back to Science Fantastic with Professor Michio Kaku. Before the break, we had a question about white holes. So let me explain. First of all, the laws of physics can run forward or backwards in time. For example, if I get a motion picture and I reverse the direction of time, then, well, bizarre things happen. Food comes out of your mouth and reforms to give you breakfast right in front of you. Dead people come out of graves and reassemble to become living people. So if you ran the videotape backwards, it would be very strange, but possible. Unlikely, highly unlikely that food will come out of your mouth and reform to create the fried egg that you had this morning, but possible. So if you have a black hole that absorbs matter like a vacuum cleaner, then a white hole should also be possible. Unlikely, but possible. But we've looked for white holes and we have not found any at all. But white holes are actually rather convenient, because if everything falls into a black hole, then maybe it spews out the other end as a white hole in another universe. Now, this idea was actually made possible by Einstein himself. In 1935, he asked himself a simple question. If you fall into a black hole, does all matter basically die at that point? What happens to the matter? Maybe it funnels out into another universe. So think of a black hole as being a funnel. A funnel where everything comes in, nothing comes out. But on the other end of the funnel, there's a reverse funnel that's upside down and is attached to the original funnel. So you have two funnels. One funnel, which is the black hole, which absorbs everything, and the other funnel shoots out matter, and that's a white hole. And then several of my colleagues have said, maybe that's the Big Bang. Maybe the Big Bang is really connected to a parent universe. Now, as bizarre as this sounds, this is compatible with an idea called inflation. And inflation, in turn, is the leading theory of the Big Bang. It turns out that, Alan Guth at MIT proposed the idea of inflation several decades ago. It fits the data. He may eventually win the Nobel Prize for this theory called inflation, which says that our universe can peel off baby universes. So think of a soap bubble, and the soap bubble can peel off baby soap bubbles, and you have this continual peeling off of baby universes. In other words, Big Bangs are happening all the time. Every time you have a peeling off of a baby universe, a black hole becomes a white hole. As preposterous as this sounds, it is compatible with all the data. When you look at the data from our Big Bang, it is compatible with the idea that these Big Bangs happen all the time. Now, does that prove it? No. It only shows that our particular universe seems to have originated from a peeling process from a parent universe, but it is not proof. Proof, we may have to go to another satellite called LISA, Laser Interferometry Space Antenna, which is going to be a gravity wave detector in outer space, which may give us baby pictures of the instant of creation. The instant of creation, the exact microsecond when the baby universe emerged out of the womb, and the hope is we'll detect evidence of an umbilical cord that connects our baby universe to a parent universe. Sounds crazy? Yeah, but hey, this is what we do for a living. We physicists look at the data, and no matter where the data takes us, that's where we go. And so far, our data takes us in the direction of inflation, which in turn makes possible a multiverse of universes. Okay, let's move on now to the next listener phone call.
Hi, my name is Fred Kushner. I'm in Colorado. I'm not currently listening to, but I do listen to our Colorado Public Broadcasting station. And my question is, if the maximum speed limit for any object or electromagnetic radiation in space-time is the speed of light, why is it that space-time itself can expand faster than the speed of light? That would be wonderful if we could answer that question for me. I'm confused.
Okay, well, Einstein's statement that nothing can go faster than the speed of light is slightly incorrect. A more precise statement would be nothing material can go faster than the speed of light. You see, nothing can go faster than the speed of light. I repeat, nothingness can go faster than the speed of light. In other words, nothing can stretch faster than the speed of light. Now, the Big Bang was when we had this explosion of a tiny area which stretched to give us the universe of today. And that stretching process was not material. It was just emptiness. Empty space can expand faster than the speed of light. But material objects cannot go faster than the speed of light. So, for example, here's an example from my youth. When I was a kid, I used to take a flashlight, and I would sweep across the night sky with the flashlight. The flashlight went from one end of the universe to the other end of the universe, thousands and thousands of light years in the other direction. And I said to myself, now wait a minute, I just violated Einstein's theory of relativity, because the image that sweeps across the sky is going faster than the speed of light. Well, I'm a physicist now, and now I realize that, yes, the image went faster than the speed of light, but material objects, that is photons, particles of light, each particle of light did not go faster than the speed of light. Here's another example. Let's say I have a bomber that drops a whole bunch of bombs in a string, and I'm on the ground and I watch all these bombs hit the ground. Each bomb is moving very slowly as it slowly falls toward the earth. But when I look at the image point of where the bombs hit the ground and then rapidly go bum, 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 bum in a line, I realize that that can go faster than the velocity of the bomb itself. So in other words, the image can go faster than the speed of light because it's not material, but not the bomb itself. Okay, well, unfortunately, we have run out of time in this segment of Science Fantastic. Once again, you can always give us a call at 612-564-8135 and leave that question, make that comment, and perhaps you can get on national radio. Once again, this is Science Fantastic with Professor Michio Kaku.